Hi, Stu Schwartz from MasterMathMentor.com. This is video AB11. The topic is Implicit Differentiation, and it covers the AB manual pages 53 through 55. Let's review. Let's suppose we have the equation x squared plus y squared is equal to 25, and we would like to find the slope of the tangent line to the curve at the point 4, 3. As we see in the graph, we have a circle. In order to do this, we are going to have to solve for y. So, doing so, we get y squared equals 25 minus x squared, and therefore y is equal to plus or minus the square root of 25 minus x squared. When we take the derivative, we end up getting y prime is equal to plus or minus 1 over 2 times the square root of 25 minus x squared. And with the chain rule, we multiply that by negative 2x, getting plus or minus x over the square root of 25 minus x squared. We then plug in 4, and we get y prime of 4 is equal to plus or minus 4 over the square root of 25 minus 16, or plus or minus 4/3. Plus or minus means exactly that. The answer is either positive 4/3 or negative 4/3. But which one? The only way we can discern that is to actually look at the graph. And it's clear that the slope is negative. So the slope of the tangent line is negative 4/3. This technique is technically called explicit differentiation. To differentiate an expression explicitly, we first solve for y. Then we find y prime. And finally, to find the slope of the secant line at the point xy, we simply plug in x, meaning we find y prime of x. The issue of that, as we've just seen, is that we may have to rely on the graph to determine whether the answer is positive or negative. But suppose the problem was to find the slope of the tangent line to the curve x squared plus y cubed plus y equals 2 at the point 2, negative 1, as shown in the graph below. How do we do this? We'd have to solve for y. Unfortunately, pretty strong algebraic techniques are going to be needed to actually solve this equation for y. There really needs to be a better way. We now define the concept of implicit differentiation. Differentiating an equation implicitly means to take the derivative of each term with respect to some variable, whether that variable is mentioned in the equation or not. So, working with the equation x squared plus y squared equals 25, if I want to implicitly differentiate that equation with respect to t, we get 2x times the derivative of x with respect to t, that's the chain rule, plus 2y times the derivative of y with respect to t equals 0. 2x dx dt plus 2y dy dt equals 0. We could take the derivative of the equation with respect to a. We get 2x dx dA plus 2y dy dA equals 0. And we could take the derivative of the equation with respect to y, as y is mentioned in the equation. We get 2x dx dy plus 2y dy dy equals 0. In the first two examples, we introduced these extra variables, t and a, and you may be confused what they have to do with the problem. This will be fully explained in Chapter 16 on related rates, but here's a brief explanation. Let's say two friends, Ralph and Alice, decide to invest in a stock. They buy the same number of shares of stock on the same day at the same time. Let R equal the value of Ralph's stock. Let A equal the value of Alice's stock. At any time, R is equal to A. Now let T represent time. Over time, the value of the stock changes. However, dr dt, which is the rate of change of Ralph's stock, must equal dA dt, which is the rate of change of Alice's stock with respect to time. So rather than solving for y as we previously did, let's find dy dx for x squared plus y squared equals 25 at the point 43 implicitly. First step is to take the derivative of each term with respect to x. So we get 2x dx dx plus 2y dy dx is equal to 0. In step 2, we can get rid of the dx dx. Anything over itself is 1. So we have 2x plus 2y dy dx equals 0. We now plug in our point, which is 4, 3. Getting 2 times 4 plus 2 times 3 dy dx is equal to 0. And now we can solve for dy dx, which is equal to negative 8 over 6, or negative 4/3, the same result we got on the previous slide. In step 3, we plugged in the point 4, 3. However, if we go back to step 2, which stated that 2y dy dx is equal to negative 2x, we could solve this for dy dx, which is equal to negative x over y. This is a formula for dy dx. We now show 4 points, A, B, C, and D, which are on the circle. We can find the slope of the tangent line to the circle at those points because we have a formula for the derivative, dy dx equals negative x over y. So at the point 3, negative 4, the derivative is 3/4. In B, at the point negative 2 square root of 21, dy dx equals 2 over the square root of 21. In C, at the point 0, negative 5, dy dx is equal to 0, which means that there's a horizontal tangent line. And finally in D, at the point negative 5, 0, dy dx does not exist. That makes sense because the tangent line is vertical, and vertical lines have no slope. In problems 1 through 6, you are given equations and points. You are asked to find the value of the derivative dy dx at those points and to do it implicitly. Notice that only in problems 1, 2, and 6 is it relatively easy to solve for y so that you can confirm your answer graphically. In problem 1, we have x squared minus y squared equals 16 at the point 5, negative 3. Differentiating implicitly, we get 2x dx dx minus 2y dy dx equals 0. Since dx dx is equal to 1, we plug in the point 5, negative 3, getting 10 plus 6 dy dx equals 0, and dy dx is equal to negative 5/3. Number 2, xy plus y equals 9 at the point 2, 3. We could do this explicitly by factoring out a y and solving for y, but let's just do it implicitly. xy is a product, so we get x dy dx plus y dx dx plus dy dx equals 0. Again, dx dx is equal to 1, and we get, as we plug in the 0.23, we get 2 dy dx plus 3 plus dy dx equals 0, and 3 dy dx equals negative 3, and therefore dy dx equals negative 1. Number 3, x squared y plus xy squared equals 2x at the point 1, 1. We have the sum of two expressions which are products. So we get x squared dy dx plus y times 2x dx dx plus 2x times 2y dy dx plus y squared dx dx is equal to 2 dx dx. Since dx dx is equal to 1, we get dy dx plus 2 plus 2 dy dx plus 1 is equal to 2. And that gives 3 dy dx equals negative 1, and dy dx is equal to negative 1/3. Number 4, y plus the square root of xy is equal to 4 at the point 2, 2. We will consider the square root of xy to the 1/2. And therefore, differentiating implicitly, we get dy dx plus 1/2 the square root of xy times the derivative of xy, which is a product. X dy dx plus y dx dx is equal to 0. Dx dx is equal to 1, and plugging in the point 2, 2, we get dy dx plus 1/4 times the quantity 2 dy dx plus 2 is equal to 0. I'm going to multiply everything by 4 to get 4 dy dx plus 2 dy dx plus 2 is equal to 0, and therefore 6 dy dx equals negative 2, and dy dx equals negative 1/3. In the previous problems, any expressions with x involved writing dx dx. You may wonder why, since dx dx is 1, and multiplying anything by 1 doesn't change it. However, you have to be careful, as we will see in problem number 5. Number 5 reads, quantity x plus y, quantity squared plus y equals 15 at the point negative 3, negative 1. First, we use the power rule. 2 times x plus y times the derivative of x plus y, which is dx dx plus dy dx. Plus dy dx equals 0. Here, dx dx is 1, but it is added, and therefore does not cancel. It is needed to be written. So plugging in the point, we get 2 times negative 4 times 1 plus dy dx plus dy dx equals 0. That gets us to negative 8 minus 8 dy dx plus dy dx equals 0, and therefore dy dx is equal to negative 8/7. Number 6 reads x squared plus 4y squared equals 4 at the point 2, 0. Differentiating implicitly, we get 2x dx dx plus 8y dy dx equals 0. Plugging in, we get 4 plus 0 dy dx equals 0, and dy dx equals negative 4 over 0. Anything over 0 does not exist, so the derivative does not exist. This is confirmed graphically. The graph of the equation is an ellipse, and at the point 2, 0, the tangent line is vertical, and vertical lines have slopes that do not exist. In 7 and 8, you are asked to find the derivative dy dx, but you are not given a point. You are to find the formula for dy dx. It should be clear that solving for y in both cases is very difficult, and implicit differentiation is the method of choice. In number 7, sine of xy equals x. Taking the derivative of sine of xy, we get cosine of xy times the derivative of xy, which is a product rule, and we get x dy dx plus y, and that is equal to 1. Technically dx dx, but I'm not going to write that anymore. So we end up getting x dy dx plus y is equal to 1 over cosine of xy. 1 over the cosine is equal to the secant. So therefore dy dx is equal to secant of xy minus y all divided by x. In number 8, tangent of x plus y is equal to x. The derivative of tangent is secant squared of x plus y times the derivative of x plus y, which is 1 plus dy dx, and that is equal to 1. So we end up with 1 plus dy dx equals 1 over secant squared of x plus y. 1 over secant squared is cosine squared of x plus y, and therefore dy dx is cosine squared of x plus y minus 1. In 9 and 10, you are asked to take the equations and find the second derivative, d squared y over dx squared. We could solve for y relatively easily on both equations, but there would be plus or minuses involved, and then the second derivative could get messy. So we're going to attack the problem implicitly. In number 9, we have x squared plus y squared equals 100. Taking the derivative implicitly, we get 2x plus 2y dy dx equals 0, and dy dx equals negative x over y. To take the second derivative, we have a quotient. We square the bottom, and the numerator is y times the derivative of negative x, which is negative 1, minus negative x times the derivative of the denominator, which is dy dx. So we're left with, in the numerator, negative y plus x times negative x over y. This is a complex fraction, so we must multiply top and bottom by y over y. And we're left with negative y squared minus x squared over y cubed. However, since x squared plus y squared equals 100, negative y squared minus x squared is negative 100, and our second derivative is negative 100 over y cubed. Number 10 reads y squared equals 9x. Taking the derivative implicitly, we get 2y dy dx is equal to 9, or dy dx is equal to 9 over 2y. So again, we have a quotient rule. To take the second derivative, we square the bottom, and upstairs we get 2y times the derivative of 9, which is 0, minus 9 times the derivative of 2y, which is 2 dy dx. But realizing that dy dx is equal to 9 over 2y, we get negative 9 times 9 over 2y all over 2y squared. Again, we will clear out the complex fraction by multiplying by 2y over 2y, and our second derivative is equal to negative 81 over 4y to the third. Notice that problems 9 and 10 involve clearing complex fractions. This is an important skill in AP Calculus, and if you are weak in this area, you will find that on page 269 of your manual there is a review. Check it out and make sure that you can work easily with complex fractions. In problems 11 and 12, you are given two equations, and you are asked to find the equation of the line tangent to the curve at the given points. Notice that in each problem it would be almost impossible to solve for y, so again we will handle the problem implicitly. In number 11, we have the square root of x plus the square root of y minus 1 is equal to y. Taking the derivative, we get 1 over 2 square root of x plus 1 over 2 square root of y dy dx. The derivative of 1 is 0, and that is equal to dy dx. At this point, we'll plug in the point 0.94, getting 1/6 plus 1/4 dy dx equals dy dx. Let's multiply every term by 12 to clear the fractions. And we're left with 2 plus 3 dy dx is equal to 12 dy dx, and dy dx is equal to 2/9. So our tangent line is y minus 4 is equal to 2/9 x minus 9. You cannot confirm this graphically because you cannot solve for y. However, I am using an Apple application called Grapher, which allows me to graph equations that are not solved for y. So we can see the blue curve, and we can see the tangent line in red that indeed is tangent at the point 0.94. In number 12, we have the complicated equation x squared plus y squared, quantity squared, is equal to 4x squared y, and we want the equation of the tangent line at the point 1, 1. Using the power rule, we get 2x squared plus y squared times the derivative of x squared plus y squared, which is 2x plus 2y dy dx, is equal to 4, and now the derivative of xy involves a product rule, x squared dy dx, plus y times 2x. It is easier now to plug in the point 1, 1 than to solve for dy dx. So we get 2 times 1 plus 1 times 2 plus 2 dy dx, and that is equal to 4 quantity dy dx plus 2. That comes down to 8 plus 8 dy dx is equal to 4 dy dx plus 8, and therefore we get 4 dy dx equals 0, and dy dx is equal to 0. So the tangent line is simply the line y equals 1. Confirming using my Mac Grapher program, the name of the complicated graph is called a two-leaf folium, and it is clear that the red line is tangent to the curve and is a horizontal line. In 13, you are given an equation, 25x squared plus 16y squared plus 200x minus 160y plus 400 is equal to 0. And you are asked to find points on the graph where there are horizontal and vertical tangent lines. We could attack this by solving for y. We would have to complete the square, and that would take some time. It's easier to do this problem implicitly. Rather than use my grapher to confirm my calculus answers, let's reverse things. I graphed the function, and it appears to be an ellipse. And it appears that there are two horizontal points of tangency at the point -4, 0 and the point -4, 10. And it appears also that there are two vertical points of tangency, 0, 5 and -8, 5. Let's start by taking the derivative. We do the work implicitly and get 50x plus 32y dy dx plus 200 minus 160 dy dx equals 0. That leaves us with dy dx, quantity 160 minus 32y is equal to 50x plus 200, and dy dx is equal to 50x plus 200 all over 160 minus 32y. To find horizontal tangents, the derivative must be equal to 0. And since the derivative is 50x plus 200 over 160 minus 32y, we set the numerator equal to 0. 50x plus 200 is equal to 0, and x is equal to -4. So that is the x-coordinate where there are horizontal tangents. To find the y-coordinate, we plug x equals -4 into the original expression, getting 400 plus 16y squared minus 800 minus 160y plus 400 is equal to 0. That factors into 16y times the quantity y minus 10, and therefore we get y is equal to 0 and y equals 10. So we confirm that the horizontal tangents are at the point -4, 0 and -4, 10. To find vertical tangents, we look at the derivative 50x plus 200 over 160 minus 32y. Vertical tangents occur when the derivative is undefined, and that occurs when the denominator of the derivative equals 0. So we set 160 minus 32y equals 0 and get y is equal to 5. To get the x-coordinates, we plug y equals 5 into the original expression, getting 25x squared plus 400 plus 200x minus 800 plus 400 equals 0. That factors into 25x times the quantity x plus 8 equals 0, getting x is equal to 0 and x equals -8. So we confirm our vertical tangents are at the points 0, 5 and -8, 5.